The world of telecommunications is a complex and quickly evolving environment. Complex systems and new technologies are continually introduced in telecommunication systems. In order to fully understand these complex systems and new technologies, a solid background of the basic fundamentals of telecommunications is necessary. Let's start by exploring how electrical signals are used to communicate a message. Electrical signals, as well as physical signals, such as sounds, vary in certain ways to communicate a message. These signals cannot be seen, but they can be graphically represented by waveforms. Shortly, we will take a trip to a laboratory where modern equipment can display electrical waveforms. The first thing we will do in the lab is provide an explanation of waveforms and discuss the characteristics of a waveform. Now, once waveforms are fully understood, we will look at the process of converting sound waves into electrical waveforms. This process will be discussed using a modern microphone and also a carbon particle microphone. To complete our trip to the lab, we will examine how load coils minimize signal loss. Many people often wonder what electrical waveforms look like and how they portray the sounds we hear and make. Let's take a look at a good analogy to help understand waveforms. When a stone is cast into a calm body of water, we see waves traveling outward in all directions from the source of the disturbance. Now, if we were able to see a side view of the waves made by that pebble, we would see that the waves were a series of peaks and valleys. The water piled up in the peaks, creating the low points, the valleys. If we were able to see sound waves, we would see something similar. The dots in this picture represent molecules in the air. When we speak, the air molecules are pushed together into areas called compressions. Leaving areas called rarefactions that have relatively few molecules. Together, a compression and a rarefaction make up a sound wave. We can't see these sound waves in the air. However, if we convert the sound waves into electrical energy, we can see them with the aid of an oscilloscope. With the oscilloscope, we can demonstrate the properties of both sound waves and the electrical waveforms that the sound has been converted into. We'll learn in a moment that waveforms can get pretty complicated. So let's start with a waveform that represents one frequency. It's called a pure tone. Now, the waveform actually starts at this line. This is called the reference line. As you can see, it moves both above and below the reference line. This defines one cycle. Now, let's listen to a pure tone. Unfortunately, the oscilloscope screen is too small to show 1,000 cycles, but we can adjust the scope to show only one of the cycles like we have here. Now, watch what happens when I increase the frequency of the tone from 1,000 cycles per second to 2,000. Okay? That is 2,000 cycles. We doubled the frequency of the tone, so we see twice as many cycles on the scope. Now, if we go to 5,000 cycles per second, we will have increased the frequency 5 times. So we see 5 cycles on the scope. We've just demonstrated the first important characteristic of sound waves and electrical waveforms, frequency. The higher the frequency of the sound, the more cycles per second. Now, let's examine the second important characteristic of waveforms, amplitude. Now, we want you to watch what happens when we increase and decrease the loudness of the test signal. As the loudness of the test signal is increased, we see that the waveform travels farther away from the reference line. This is an increase in the amplitude of the waveform. As the loudness of the test signal is decreased, the waveform comes closer to the reference line. This is a decrease in amplitude. Amplitude is the measure of the strength of a signal. With electrical waveforms, amplitude is measured in volts. And now, let's look at how a microphone converts sound waves into electrical waves. This part of the microphone is called the diaphragm. The diaphragm vibrates when sound waves come into contact with it. Attached to the diaphragm is a coil of wire called a voice coil. The voice coil sits inside of this magnet. When sound waves hit the diaphragm, it depresses, moving the attached coil. When the voice coil vibrates inside of the magnet, electrical signals are generated. In other words, when the diaphragm moves in and out, an electrical waveform is created. Once again, let's turn to the oscilloscope and see the electrical signals that are created when I talk into a microphone. The signal produced by the microphone is not strong enough by itself to register on the scope. So I'm connecting this amplifier between the two to strengthen or to amplify the signal. I'll simply turn on the amplifier, and of course it's connected to the oscilloscope. Hello? This is what my voice looks like on the oscilloscope. Notice that these waveforms are much more jagged and irregular than the waveforms we have seen so far. That's because my voice is actually a mixture of different frequencies. We just saw that the microphone that uses a magnet and voice coil has to be amplified. However, amplifiers didn't exist when Bell invented the telephone. What did he use to convert sound waves into electrical signals that were strong enough to carry the telephone conversations? A carbon particle microphone. The carbon particle microphone was invented by Thomas Edison in 1890. Carbon particles have a unique property. When they are compressed, their resistance to electricity decreases. When pressure is released, their resistance to electricity increases. As you can see, when sound waves hit the microphone, there are changes in resistance to electricity. Bell used a power source in conjunction with the carbon particle microphone. Used together, they are able to produce a strong electrical signal which doesn't require amplification in order to register on our scope. You can see that when we turn on the power and speak into the carbon particle microphone, a strong signal is created. Of course, the farther a signal must travel, the weaker it gets. The farther away your listener is, the weaker your voice sounds. Likewise, the farther the telephone signal must travel, the lower its amplitude, that is, its voltage, becomes. Eventually, even a strong telephone signal must be amplified. We said that the amplifiers we know today didn't exist when Bell invented the telephone. How did he solve the problem of how to strengthen the signal? He did so with a device called a load coil. Before amplifiers were invented, load coils were used to minimize the amount of signal loss. This device matches the impedance of transmission lines to minimize signal loss. Let's look at how the load coil affects the electrical signal. Here we see a waveform produced by the signal generator before and after going through load coils. Notice that the load coil limits the amount of signal passing through it. This is how impedance is matched on telephone lines. I hope this short trip to the lab has cleared up some questions about waveforms and how telephone signals are created and transmitted. Remember, all motion, whether in the air, in water, or electrical, can be represented as waveforms. Please return to the computer so you can learn more about waveforms.
The ever-improving world of telecommunications. It's the Telessentials Curriculum Newsreel. In this episode, we will present the major developments and innovations which have contributed to the evolution of telecommunications.
Today, the world of telecommunications involves the most sophisticated technology, enabling you to reach a friend across the country or around the world. The modern telephone system didn't happen overnight. It's the result of over 100 years of innovations. Let's now trace back to those many important developments which make up the evolution of telecommunications. In 1876, telephone history was made during an experiment conducted by Alexander Graham Bell. Bell spilled acid on his trousers and he cried out for help. His voice was carried into the next room through electrical current. His assistant was amazed to hear these immortal words. And thus the telephone was invented. But back then, telephones were connected by separate lines. So somebody calling 20 people needed 20 separate lines. Obviously, a central system was needed that could connect or switch any of those telephones together using just one line. Just 2 years after the first telephone patent, manual switching was introduced. Now, one line through the switchboard could connect one telephone to any other. In time, operators connected or switched hundreds of lines from one central switchboard. But not everyone was happy with this situation. A.B. Strauger, a Missouri undertaker and inventor, discovered that the local switchboard operator was sending his business calls to a competitor. Outraged, Strauger invented the first automatic switching system in 1892. The step-by-step, or Strauger system, added a rotary dial to the telephone set. Dial pulses were sent directly through a series of switches to connect the call. By the 1920s, people were able to directly dial across the country the step-by-step way. But the large switches of the step-by-step system were costly to operate and maintain, and calls were often blocked or interrupted during dialing. Taking the place of step-by-step's slow switches, the crossbar system was introduced in 1938. The crossbar was able to switch a phone conversation in just tenths of a second and with less chance of blocking. Soon the crossbar systems were providing international direct dialing and many other services. Crossbar switches were more reliable than step-by-step switches. This made them less expensive to operate and maintain. Later, the crossbar system became faster and more efficient, thanks to the development of transistors and computer technology. The era of electronic telephone switching began in 1965 with the introduction of the electronic switching system, sometimes called the ESS. With fewer mechanical parts, the ESS systems used electronics and computer processors to minimize the need for mechanical relays. The computer technology of the ESS could quickly switch a call many times faster than before. Since the 1970s, digital ESS systems used distributed processing of digital signals. This integrated switching and transmission equipment used one end-to-end digital network. With digital technology, the newer ESS models provided the fastest, most efficient, and accurate switching of both voice and data. Through the years, switching systems have undergone many changes. At the same time, new methods have been developed for transmitting calls between the switching machines. Let's step back and look at how transmission media have evolved. In the early days of the telephone, a call was connected by two wires, called an open wire line. This involved two uninsulated wires spaced apart so they would not touch. The open wire lines were very susceptible to noise and corrosion. To solve this problem, wires were coated with insulation and twisted together into pairs. This reduced corrosion and noise interference. This more reliable line was called a twisted pair. To connect calls from one central office to another, trunks were developed. Trunks were soon improved with 4 wires and amplifiers so that calls could be sent greater distances. Eventually, a more efficient way of using trunks was discovered. More than one call could be carried by one pair of wires using a process called multiplexing. With multiplexing, several calls were combined and sent over one trunk. This enabled the calls to use the entire bandwidth or frequency range of the trunk. With multiplexing, one trunk can now carry 24 to 48 calls at the same time, instead of just one call. A major problem with transmission by wire was attenuation, the loss of signal strength over distance. Wire was not the best medium for sending high frequencies over great distances. New methods were needed that limit attenuation by transmitting without the use of wires. Today, a signal can be beamed through the sky by terrestrial microwave radio. The microwave radio signal is similar to FM radio, except that it is beamed directly from one antenna to another. A microwave radio signal can carry more calls than wire with less signal loss. Microwave radio signals also help us communicate around the globe, thanks to satellite transmission. A ground station beams a signal up to the orbiting satellite, The signal can then be retransmitted to another ground station located in another part of the world. Another transmission marvel is light guide cable, also called fiber optics. Electrical signals are converted into light and then beamed down a glass fiber. The result? Higher communication capacity and lower maintenance costs. Yes, the world has changed since Alexander Graham Bell's first experiment. The telephone has brought people all around the world closer together. We can now communicate with each other much better and in more ways than ever before. You can be sure that more improvements are in the making. So stay tuned for new developments as the evolution of telecommunications continues. Please return to the computer so you can learn more about the evolution of telecommunications.
Ladies and gentlemen, Alexander Graham Bell.
Modern telephone systems evolved from the first simple telephone to advanced telephones and other types of equipment that improved communication tremendously. In this program, I'll show you an example of one of the first telephones. I'll also show you some examples of telephones and explain their major components. Then we will visit a central office where we'll see equipment used for processing telephone calls. We'll see how the telephones in your home or office receive power and how telephone lines connect to other telephone lines for calls. After touring a central office, we'll look at how the components of the telephone set and the components of a central office work together when you make telephone calls. Finally, we'll talk about different types of telephone services used by individuals and businesses. Let's take a look now at 3 telephones. In some ways, they are similar, and in other ways, they are very different. Through the years, telephones came in many sizes, shapes, and colors, but they all contain the same basic components. This is one of the earliest telephone sets. With this type of phone, the transmitter and receiver are on separate parts of the phone. In modern phones, both the transmitter and receiver are in the handset. Let's take a look inside. The transmitter is often a carbon particle microphone. Remember, the carbon particle microphone was used in very early telephones and is still used today. The carbon particle microphone does not require an amplifier, but most telephones manufactured after 1980 have an electromagnetic microphone. This type needs an amplifier circuit in the telephone set. At the other end of the handset is the receiver. It's basically a speaker that converts electrical signals into sound. It's similar to any other speaker that you would find in a radio or stereo. In these early-style telephones, the receiver hangs on a switch hook. On new telephones, however, the receiver is in the handset. Both the receiver and the transmitter connect to the hybrid coil. The hybrid coil combines a 4-wire circuit in the handset into a 2-wire circuit that connects to the central office. The hybrid coil incorporates a device called the balancing network. This allows someone speaking into the transmitter to hear their own voice in the receiver at a volume close to the other person's voice, so the person speaking can make sure they don't speak too loudly or softly. The hybrid coil and the balancing network work together. Both devices allow full duplex transmission along the 2 wires between the telephone and the central office. Full duplex means that signals are transmitted in both directions at the same time. This conserves the number of wires required to serve telephone customers. The switch hook gets its name from the hook on this old telephone. The receiver hangs on it. When the receiver is on hook, the electrical circuit to the central office is not complete. When the bell rings, you lift the receiver. When the receiver is off hook, the circuit to the central office closes and the call can be completed. On an old telephone, you turn a magneto crank on the set. This generates a current to the central office indicating that you want to make a call. With modern telephones, you lift the handset, the switch hook goes off hook, and the circuit is completed to the central office. This indicates that you wish to make a call. In this rotary dial telephone, the ringer is an electromechanical bell. It rings when alternating current is applied to the line by the telephone company. On most telephones made after 1980, the ringer is an electronic tone ringer as shown here. Previously, telephones used an electromechanical bell. Let's say that you want to make a call. In the old days, you couldn't dial. The operator had to connect you. Today, however, you can use rotary dial or push button. The rotary dial produces pulses. If a person dials an 8, the pulses are generated as the rotary dial returns to its original position. The central office interprets these pulses to connect your call. Rotary dial telephones produce about 10 pulses per second. The push-button dialing mechanism creates tones of different frequencies. As you can see, this set of buttons, called the keypad, has the numbers 0 through 9 and 2 symbols, the asterisk and the pound sign. Some keypads have other symbols and letters, but we'll focus on this one, since in this type, each number or symbol has 2 tones or frequencies assigned to it. So this method of dialing is technically called dual-tone multi-frequency. You probably know it as touch tone. Pressing one of the numbers causes 2 tones to be generated by the electronic circuit in the telephone set. When these tones reach the central office, the tones are interpreted as a digit. The central office needs these digits to determine the destination of the call. The touch tone method of dialing is much faster than the rotary dialing method. Rotary dialing takes as long as 1 second per digit dialed. Many newer services offered by telephone companies require touch-tone signals. Well, now that you understand more about the telephone set itself, let's find out how the telephone gets its electrical power. We will do this by taking a tour through a central telephone office. Here we'll look at devices commonly found in central offices. This equipment supplies power to all of the telephone lines served by this central office. It also supplies power to the switching equipment. These batteries power the switching system and all of the telephones when there's an electrical power failure. This string of batteries supplies 48 volts DC. Normally, the batteries are continuously charged by the charging system. The charging system powers the switching equipment and all of the telephones. This system works very much like the charging system found in an automobile. When there's an electrical power failure, the batteries still supply power, but the batteries can't power this equipment for very long. Other backup power sources are generators. Many central offices have standby engine generators that start up a few minutes after an electrical power failure. The generator powers the central office and the batteries until commercial power is returned. Now that we've seen the power supply equipment, let's take a look at a switching machine. A switching machine has 3 main functions: logic, command, and monitoring, also known as supervision. All switching machines use these functions to connect lines and trunks on demand in any combination. The switching machine is usually called a switch. In addition to the power supply and the switch, another important part of the central office is the transmission equipment. This equipment is used when telephone signals must travel great distances. Signals are transmitted in various forms. They can be sent through copper wires, fiber optic cables, or microwave. Here you can see microwave radio towers and radio antennas. Transmission components include multiplexers, modulators, amplifiers, signal converters, and repeaters. Multiplexers combine signals to form one composite signal for transmission. Modulators convert a signal from one form to another. The purpose is to make the signal suitable for the transmission medium being used. Transmission equipment also includes amplifiers, which are used to strengthen signals so they can be sent great distances. Another component of transmission are converters. Analog to digital converters change analog signals to digital signals for transmission over digital facilities. As signals travel, they lose their strength, so they are periodically regenerated. All of this transmission equipment is connected to the switching equipment via a distributing frame. A distributing frame terminates wires in an orderly, structured fashion so other wires can be attached. There is a main distributing frame connecting outside lines coming from subscribers to the central office equipment. This MDF has lightning protector devices called heat coils. If lightning strikes outside lines, the switching equipment won't be damaged. Trunk cables from other offices also connect to the MDF. The trunk distributing frame connects trunk switch frames to trunk circuits. Generally, both line and trunk cables terminate on the MDF. Cables that contain lines from the cable entrance facility are routed up through different floors to the switching and transmission equipment. They're called riser cables. All of the equipment you've seen in this central office requires specific environmental support systems. A cooling system keeps the air at an appropriate temperature. Fan systems help ventilate the central office, lower humidity, and serve as a backup for the cooling system. Air filtering systems minimize dust and gases. This concludes our tour of the central office. All of the equipment we saw helps to make each telephone call as fast, clear, and efficient as possible. Up to this point, you've seen how the phones work. You've also seen a central office, but how do they all work together? Throughout a telephone call, status and alerting messages are sent back and forth from the telephone sets and the central office equipment. Sending these messages back and forth between equipment is known as signaling. Let's look at the basic process of call origination and disconnection. The first step in call origination is when you pick up the handset. Now, a circuit is completed between the telephone set and the central office equipment. As the switch monitors the lines, it detects the completed circuit. This is called request for service. If the switching machine can handle this request for service, dial tone is sent to the person's receiver. After dial tone is received, you dial the phone number. The digits are sent to a register in the central office. The switching machine analyzes the digits as they are received by the register. It now knows where to direct the call. The switching system checks to see if that phone is busy. If not, ringing voltage is sent from the ring generator in the switching system. Audible ringing sound is also sent back to the person making the call to let this person know the line is being alerted. Let's say that Sally calls Fred. When Fred picks up the phone, several things happen. The switch removes ringing voltage from the terminating line and removes the audible ringing from the originating line. It then establishes a talking connection. At the end of the conversation, someone hangs up. This is also known as going on hook. In most telephone systems, a device in the central office switching system keeps the phone connected for a short time after someone hangs up. This is called open service interval protection. It exists in case someone accidentally pushes on the switch hook, or if there is some technical problem in the lines. The connection is usually only maintained a few seconds in this condition. If you leave the telephone on hook for more than a few seconds, devices in the switching system consider the conversation over, and the lines are disconnected. Switching equipment is made available for other calls. This is known as call disconnection. This is what happens when placing a telephone call. Now, let's look at some types of telephone service that are offered to businesses and private individuals. The most common service which individuals subscribe to is called basic service. There are more complex telephone services available which address the needs of businesses. We will explore 4 main types of telephone services. The first type of telephone service is the most basic. It is often referred to as plain old telephone service, or POTS. This service consists of several things: a standard rotary dial or touch-tone phone, and a line from the telephone to the central office. You also get a telephone number assigned in the central office and usually a listing in a directory. Another type of telephone service is a key system. A key system has 2 or more telephone sets. A key system is usually purchased equipment which a business owns and maintains. Key telephone sets usually have push buttons with extension numbers on them. Key system phones are also known as key stations. Sometimes in a key system, the telephone lines are concentrated. This means there are more telephones than there are outside lines. The key system controller links the telephone sets together and connects the telephones to the outside lines. If you use a key system phone, you push the appropriate buttons or keys. You can only use the lines shown on the keys of that phone. But when you answer a call, you can use your phone to answer calls from any line. Let's suppose that Sally calls Fred again. You can transfer that call using the key system telephone. First, you put Sally on hold. Then you call Fred and tell him he has a call on line 2. How does a PBX differ from a key system? Are there any differences? Let's take a look at a system that's similar to a key system. A private branch exchange, or PBX, is another type of telephone system. Like the key system, it's usually owned and maintained by the same business. A PBX is similar to a miniature version of a central office switching machine. Lines from the telephone sets run to the PBX. Concentration can be used with a PBX so that you can have 500 phones and only 100 lines to the central office. Extensions within the company are usually reached by dialing numbers assigned to the sets. When you pick up the phone, you hear dial tone from the PBX. You can call another extension, but if you want to make an outside call, dial a single digit. The PBX connects you to an available outside line. Now you hear dial tone from the central office. Now you can dial the number. The last type of telephone system I will discuss is the central exchange, or Centrex system. With Centrex service, a business can get PBX-like services directly from the central office. However, with Centrex, every telephone set has a line to the central office. There are no switching machines on the premises of the business. As with the PBX, you can reach an extension simply by dialing the number. Devices in the central office keep track of the Centrex group and will automatically connect you to the 7-digit number, even though only 3 or 4 digits were dialed. One advantage of Centrex is having advanced features that may not be available with many PBXs. And with Centrex, maintenance of equipment is the responsibility of the telephone company. Sometimes in businesses, there are several types of services combined. For example, a company can have a key system and a PBX and also subscribe to Centrex services. As you've seen, the basic components of telephone sets have not changed very much through the years, but the advanced telephone services have more capabilities than ever before. Since central office equipment is more complex, it connects and disconnects calls efficiently with tremendous speed. There's no doubt that the modern telephone system will continue to evolve with greater capabilities to meet the needs of customers. Please return to your computer to continue this lesson. When I compare my first invention with today's telephones, it's obvious that many changes have taken place. In fact, the entire telephone system has grown into a complex and integrated group of devices that can connect your telephone to almost any other telephone. This integrated system is called the Public Switch Telephone Network. This program presents an overview of the Public Switch Telephone Network and shows how the network can send a call from this telephone to a phone across the street or across the country. A network is nothing more than a collection of interconnected devices that wish to communicate. One familiar example of a network is our system of roads and highways. In a small town, most people live out of town on rural roads. A network of roads connects the local residents with the main streets leading to town. A main street usually connects this town with other nearby towns. This network of roads is adequate for local traveling. However, for traveling longer distances, a more efficient route would be a highway or interstate. These are designed with limited access to better handle long-distance transportation. The public switch telephone network is similar to our network of roads. Each component of the network is designed to carry a specific type of telephone traffic. All of these components interconnect so that your call can reach its destination by the most efficient route available. Let's look at how the public switch telephone network operates. Local secondary roads are connected to other roads that lead to town. Likewise, telephones are connected with two wires to the main telephone cables that lead to the central office. The central office is the location where the calls in an area are switched. Electricity flows on one wire from the central office to your telephone. It then flows back to the central office on the other wire to complete a circuit. These wires are sometimes called the tip and ring wires. This terminology comes from the switchboard days when one wire was connected to the tip and the other to the ring of a switchboard plug. This pair of wires is also referred to as the local loop. The term local loop commonly refers to all of the wires which connect the central office to all of the local subscribers' telephones. The local loop is the first rung of the public switch telephone network. Connections in the local loop are made by using 300, 600, or even 900 pair cables extended from the central office. Subscribers are connected to the pairs of wires in these cables. Usually, large cables leading from the central office are spliced to smaller cables so that all of the subscribers are connected to the central office. The many pairs of wires in a telephone cable are coded and numbered according to a color coding system. With this system, each twisted pair in a telephone cable is identified and organized systematically. When a subscriber reports a problem with the telephone line, technicians can use records to locate and test the specific pair. The color coding technique works by grouping pairs in special color combinations. The first 5 pairs are white-blue, white-orange, white-green, white-brown, and white-slate. The second 5 pairs replace the white with red. The third 5 use black. The fourth uses yellow, and the fifth uses violet. This color coding scheme allows for organizing and tracing all of the wires in the local loop. To connect the telephone traffic from one central office to another central office, a special set of wires is used. This set of wires is called a trunk. Most trunk circuits use 4 wires for the voice path. This makes it easier to amplify the signal so that trunks can extend over greater distances. To accommodate a high volume of local calls, 2 central offices are usually connected by a number of trunks called a direct trunk group. Direct trunk groups are practical for nearby central offices with a high volume of calls between them. If the volume of calls between 2 central offices is low, they can be connected through another switching office called a tandem office. Tandem offices connect calls between central offices by a tandem trunk group. The term tandem refers to the function of connecting switching offices and not to a specific type of switching machine. For example, if the switch in this office connects two central offices and it also switches calls to its local loop, this office serves as both a tandem office and a central office. Sometimes the most direct route for a call is already occupied, as shown here. Switches can then select an alternate route through a tandem office. This procedure is called automatic alternate routing. The first selected route for a call is called the primary route. When the primary route is busy, a secondary route is automatically selected. If necessary, a third or fourth route can be chosen. The call may be switched through a series of tandem offices before reaching its destination central office. Automatic alternate routing helps the network prevent a call from being blocked or interrupted during switching. As calls are connected at a central office, switches record the usage of each trunk group. This information helps engineers make routing decisions. Local loops, tandem offices, and the trunks connecting local offices make up the local network of the public switched telephone network. The local network actually consists of many telephone companies called local exchange carriers. Each local exchange carrier is responsible for the local switching in its area. If a call is requested outside the local network, the local exchange carrier will connect the call to one of the toll networks of the public switched telephone network. The toll networks refer to the offices and trunks which receive calls from the local network and then carry them greater distances, usually for an additional charge. The toll network was reshaped by the divestiture ruling in 1984. While the local exchange carriers can function in their local areas, long-distance service is now provided by competitive carriers. These long-distance carriers are called inter-exchange carriers. The local exchange carrier is obligated to connect a subscriber to the inter-exchange carrier of his choice. This concept is called equal access. Each toll network is designed to connect calls using a minimum number of switching offices. This can be accomplished by computer programs in the switching machines that do alternate routing. AT&T uses Dynamic Non-Hierarchical Routing, DNHR. This is a software system included in toll network switches that makes routing decisions. Other inter-exchange carriers use similar software for making routing decisions. Dynamic non-hierarchical routing uses routing tables that are designed for each central office. The routing tables allow for different routing patterns based on time of day and day of week. In the morning hours, East Coast calls are often routed through West Coast switches to take advantage of the time difference. In the afternoon hours, West Coast calls are often routed through East Coast switches. Over time, these routing patterns may change. Engineers evaluate traffic reports to make routing decisions. One of the reasons that today's toll network operates so effectively is because of direct distance dialing. This allows a number to be dialed directly without the assistance of an operator. Direct distance dialing is possible because of the North American numbering plan implemented in 1947. With the North American numbering plan, every telephone station receives a unique 10-digit number called an address. Each address is divided into 3 codes, which tell the switching system the exact location of the dialed call. To implement the North American numbering plan, the country was divided into numbering plan areas. The numbering plan area is represented by the first 3 digits called the area code. For example, Joe's friend Lou lives near Kansas City. His area code is 816. When Joe dials Lou's number, the call is routed directly to the 816 numbering plan area. The central office connected to Lou's line is then identified from the second 3-digit code called the office code. Since Lou's office code is 555, the call is routed to the 555 central office. At the central office, the exact location of Lou's station is identified by the last 4 digits of the address. This last code is called the station code or the line code. The central office can now route Joe's call directly to Lou's telephone at home. If Joe next wants to call Sue, who lives within Joe's office code, he does not need to dial the area code. He can just dial the last 7 digits of Sue's address. The central office recognizes the first 3 digits as its own office code and knows that a local call is being dialed. Each code of a telephone address is numbered in a specific way, especially for long-distance dialing. Usually, a long-distance address is prefixed with a 1. This is called the long-distance prefix because it tells the switches that a toll call is being requested. An address may also be prefixed with a 0 to request operator assistance, such as credit card billing. This is called the operator-assisted prefix. Because of these prefixes, the area code cannot begin with the digits 1 or 0. Area codes are numbered in this way: N, which can be digits 2 through 9, and X, which are digits 0 through 9. The office code is numbered in the same way as the area code. This prevents the first digit of the office code from being interpreted as a prefix. For the line code, however, all digits from 0 through 9 may be used. Every office code for a central office can handle 10,000 station addresses. If one central office has to connect more than 10,000 stations, additional office codes will be assigned. Cities with many telephone stations, such as New York, may need 100 or more office codes to handle all of the telephone traffic. Increasingly, big cities need more than one numbering plan area. For example, New Yorkers must dial a different area code for a nearby number. When traveling by car, you use a mapped route along an interconnecting network of roads and highways. Your telephone calls also travel along routes of the local and toll networks.
As I said before, your telephone is a small part of a much larger system, the public switched telephone network. This vast collection of local loops, toll centers, and connections work together so that your call can reach almost any destination. Let's continue this overview of the public switch telephone network on your computer. By the way, there's also a more detailed discussion of the public switch telephone network in the lesson, Communication Networks. Now please return to the computer so you can learn more about the public switch telephone network.
Hello! Bits and Bytes here to discuss the computer's role in the world of telecommunications. I'll show you the parts and functions of the computer and how the computer works. The computer has 4 major functions. I'll explain these functions and show you the hardware devices the computer uses to accomplish each function. The first function is input, the instructions and data that are fed into the computer. The keyboard is one type of input device. Other input devices include a barcode reader, joystick, mouse, and a touchscreen monitor. We communicate with computers through these input devices. But how does the computer understand what we're saying? People count in base 10, the decimal numbering system, probably because we have 10 fingers. Computers count in base 2, the binary numbering system, because its language is a code of electronic pulses that are either on or off, represented as ones and zeros. These on-off pulses are called bits, short for binary digits. When we input data as numbers, letters, or symbols, the computer translates that input into its code of electronic on-off pulses. Every number, letter, and symbol that appears on the keyboard has its own code. The computer even has different codes for upper and lowercase letters. ASCII is the internationally accepted code which represents numbers, letters, and symbols with unique binary code values that the computer can understand. 1 byte, usually 8 bits, contains enough information to represent one ASCII data character. The second computer function is storage. Storage is any device or medium capable of accepting input and retaining it so that it can be returned and used when required. A floppy disk drive is one type of storage device. Other storage devices include internal memory, tape, hard disk, and optical disk. We can store or save input on various storage devices. But how is the information saved, and how much can the storage device hold? Input data is saved on storage media in its ASCII code. A floppy diskette can hold large amounts of data. A low-density floppy, like this one, can store 360K, or 360,000 letters, numbers, and symbols on one floppy. That equals over 200 typed pages. Other storage medium can hold megabytes of data, which adds up to millions of bytes of data. The third function is processing. The CPU, Central Processing Unit, performs this operation. If computers only stored information, they would not be used as heavily as they are. The strength of computers is in how they process the information you put into them. Examples of processing include checking the spelling on a long document, figuring out the budget for a company, or changing a picture. Processing uses most of the equipment inside the computer. Let's take a look at some of it. This green plane is the motherboard of the computer. It's covered with many tiny etched paths which connect various chips together. There are several types of chips on the motherboard. The most important chip is the CPU, or Central Processing Unit. This is the unit that controls the flow of information. It performs arithmetic and logic operations on the data that flows through the computer. The CPU reads the instructions and data to decide what to do and in what order. A second type of chip is the ROM chip. ROM stands for read-only memory. The ROM chips contain permanently stored instructions used by the CPU in its operations. Another type of chip you'll find in your computer is the RAM chip. RAM, Random Access Memory, is used by the CPU as a temporary storage area for data and instructions. The CPU can read or write to these chips as long as the machine has power. In older computers, RAM chips are located on the motherboard. On newer computers, most of the RAM chips are mounted on RAM cards. The last major function of the computer is output. Output is information or data transferred from memory to be presented to the user. The monitor is one type of output device. Other output devices include printers and speakers. Data is transmitted to an output device either through parallel or serial processing. Parallel processing involves transmission of all bits of a character simultaneously from the CPU to the output device. Serial processing involves transmitting each bit of a character sequentially from the CPU to an output device. Now that we've discussed the main functions of the computer, let's take a closer look at how the central processor functions. The CPU contains the brains of the computer, giving us the solutions to our problems. But how intelligent is the computer really? A computer's sole talent is to react with lightning speed to coded bursts of voltage. The computer is no smarter than the computer programmer, who must first tell it the steps to execute from beginning to end. A logical sequence of steps called an algorithm is designed to solve a problem. This algorithm is then translated into a program or set of machine instructions for the processor to follow. The Central Processing Unit, CPU, is responsible for decoding and executing machine instructions. Input to the CPU can come from an input device, such as the keyboard, or from a storage medium, such as a floppy diskette. The input is then stored in RAM. When the computer executes a program, the CPU keeps track of its place by storing the address of the next instruction. It stores this address in a special register called the program counter. The instructions from the program, which are stored in memory, RAM or ROM, are retrieved by the control unit of the computer's CPU. The CPU fetches the contents of the program counter's address. This operation is repeated until an entire instruction and the data to be operated on have been fetched by the CPU from memory. Then the CPU performs the instruction using its arithmetic and logic unit. The instructions are read and executed one at a time until all the instructions have been carried out. The results from the CPU are stored in RAM and are displayed to the user via an output device. Digital computers work in a synchronous mode of operation. This means the CPU works to the beat of a timing signal, which comes from a clock device. So far, we've learned a little about how the computer works. Now, let's explore the computer's role in telecommunications. The modern switching machines found in central offices are really special-purpose computers. The telephone is the input device. The customer inputs data, the telephone number he wants to call, into the switching machine. The processor receives the telephone number and stores it in temporary memory. The processor then processes the number to determine what service is required and how best to provide it. When a line is selected for the called party, the processor outputs a ringing signal to alert this party, and an audible ringtone is sent back to the calling party. When the called party answers, the computer sets up a two-way path so both people can talk simultaneously. Computers are everyday machines affecting all of our lives in unsuspecting ways. The alarm we wake up to, the car we drive to work, traffic lights, well, the list is endless. Every second of every day, the input, storage, process, and output functions are performed to make life more convenient all around the world. Oops, Oh, gotta go.
Hey Bob, you should see this neat animated character we created. He's going to show how computers are used in telecommunications.
Good.
Now, please return to the computer so you can learn more about computer terminology.